they did pick the one that was the least horrible, but when they put up their PR thing on their webpage, the guys were standing there, really proud of their new LEDs they put up, and there were 2 guys and 4 shadows. So it's like, yeah, that's not good lighting. So anyway, off to outreach. May 1st, yesterday we did Washington School under the clouds, but we had 263 kids show up. Tomorrow is International Astronomy Day, so all day we'll be out at Camino Real Marketplace. So set up at 9, but ready for the public at 10. I think it's going to be cloudy, but we might get some sucker holes if we're lucky. And so we'll have people showing off their scopes, and we'll have some displays. I'm sure Chrissy has some stuff going on. And we'll have some giveaways and things like that. Not a real big production. And then we're going to take a break between 4 and 7, and then set up for a star party at 7. There's a lot of lights there, but we've got some cardboard boxes we can put on some of the lights. And hopefully we'll at least get a view of the moon. And then on Sunday here, there's going to be an Astrofest here at the museum. And they're asking us to come out between 10 and 2 out by the observatory with solar scopes and looking at the moon and whatever. We can try to get Venus too, which will be fun. And then Tuesday, Telescope Tuesday, first Tuesday of the month, out there again at Camino Real. And again, we have cardboard boxes, although we'll have a fairly bright moon, so I don't know if we'll bother with that. But yeah, we usually get a fairly good crowd, especially if there's a new movie that's just come to the theater, so we're right outside of that. When Barbie opened, we had over 200 people all dressed in pink show up to that. And then Wednesday up in the San Ynez Valley, Dunn School, they want to have an astronomy night, and we're going to set up on their soccer field like we did the last time we went up there. And that's nice dark skies. Then second Saturday of every month is the star party here, so we'll be set up by the observatory down there with our scopes, and the museum will have the big scope going. Then third Fridays every month, usually at Westmont with their Keck Observatory with their 24-inch scope there. Usually a pretty nice experience. And then we're back. Refugio State Beach. Yeah, that's everybody likes that. That's a nice dark sky. And I think we can get there just by the usual way. There's been all kinds of detours because they're demolishing that huge bridge that the 101 went over the Refugio Canyon there. But I think that's now we can take the normal route to get in there and to get out. So that construction is kind of done. They were talking about having us come during the wintertime, but there was so much construction to the bridge that they didn't ask us to come. But we're back. And we've also booked with Carpinteria State Beach, hopefully with Kachuma Lake. There's some stuff going on apparently there with people quitting and not answering emails, but we should be set for just about every Saturday in July and August to be either here or up there with a star party and a slideshow. And then we have our camp out in October, which hopefully will still happen. I've emailed the people there that I'm supposed to contact and not heard back, but I have a nice sheet of paper that says we have that campsite, so we should be good there. So essentially every Friday and Saturday between June and early September we're booked, so you can always find us somewhere. Thank you.
Thank you, John. And now we'll hear from Diane Welkenbach, our events coordinator.
Thank you, Jerry. Okay, our first event for this year is going to be our potluck in June, so Friday, June 6th, and it's open to members of SBAU. So if you're not a member yet, please sign up. It's only $20. And the potluck is going to start at 5 o'clock, 5 to 7. So get your recipes ready and we'll have some fun. Thank you.
Thank you, Diane. We're moving right along here. Tessa, do you have anything you want to say to us?
I will just quickly mention to members, we still have a few more of the directories. They're only about, Pat is demonstrating them right now, my interactive assistant. And make sure you get this edition because you never know, the next one might have tariffs applied.
Thank you, Tessa. Tessa, as you know, is our secretary and leads the crowd here.
Jerry wanted to mention, we have equipment that, if you're looking for something like telescope that we do have available, there's a member advertising on Craigslist right now. It says $1,400 at the top, but he's lowered it down to even $1,200 for quite a big assembly of equipment. And we have some other telescopes and other items that we'd like to pass on. So for a little donation, you might be able to pick up a telescope.
I knew I forgot something. Tom Totten is our telescope and inventory manager and webmaster.
Thank you.
Yay.
Thank you.
Now we move on to our vice president, who will introduce our speaker for this evening.
And a couple of other stupid, silly things that I'd like to do, if you don't mind. Okay, thank you, Mr. Prez. Don't forget, I'm still a heartbeat away from your job. You know that. Oh my God, there I am on the screen here. And there's Tom Totten. And do we have people online watching this program only through this little lens? Okay, my name's Ronnie Heron, and I used to be on the radio. And now I'm vice president, and I don't even own a telescope. Tonight, Baby Galaxies Are Us, featuring from CSU San Bernardino. See if I can get all this remembered without looking down at my notes. Give me a minute here. I don't want you to stand too long. It's Dr. Maria Katy Rodriguez-Wimberly, professor who's probably very popular on the San Bernardino campus. I'm going to take my little poll. I want to know how many in the room, first-timers, newcomers, never been here before. Raise your hand.
Wow.
Enough of you. Okay, now the people who've been here before but are not members. Any repeats? Okay. Extra 10 years on your life, courtesy of the card. Now, members only. All right, you guys are going to have to talk to the ones who get them to join the club before we're out of here tonight. Because I can't think of a more fun club. And part of the reason, not only the people you've seen, and you're going to get to know if you join for $20. And I'll clue you in, there's a freebie if you go to enough of these amazing Camino Real and Refugio Beach outreaches. You do 6 of them a year? Or is it 6 a month? I think it's 6 a year.
6 a year.
It's all free.
But you have to get vetted by the museum to deal with the public. There has to be a background check.
For you to join our club for
No,
free?
to get the outreach credit, to work with the public.
Oh, okay. Do we have anybody doing that, Chuck?
Yeah, all the outreaches that got credit last year, they've all done the background checks.
Well, I happen to have been privileged to MC, to co-host, or actually, I consider co-hosting with the president, a Monday morning vlog. We long ago, I guess, disposed of the word podcast, because that's only listening. This is on YouTube. It's a whole hour. We've been doing it for over 4 years. It's 11 a.m. on Mondays, and it's called the SBAU Astro Hour. And I'm gonna pay them $20 anyway, I've decided, even though I get it free, because that's my particular piece of outreach. We're gonna be talking to a lady here in a minute, but anyway, next month, make sure you bring something good, sign up with Diane. I guess I wanna do another salad. A lot of times I just hit the deli section and let them make it and I pay for it. We're gonna become, out here at Broder Hall, across the creek, we're going to become a Golden Corral, all-you-can-eat buffet. And all you got to do is bring a covered dish. Let me quickly, before I introduce our lovely speaker from the Inland Empire, tell you what's ahead. As you've already learned, there'll be no meeting like this next month, June 6th. If you're a member, you can come. Bring something, and it'll be like the old days when we had buffets. Anybody remember the Scandia?
Oh yeah.
And the one across the street, I think, on Upper De La Vida was all Chinese. They're gone. I can't remember any others in town. Baby Galaxies coming up, but on July the 10th, which is a Thursday, put this on your calendar and your cell phone right now. We have, amazingly enough, I'm doing this without my glasses, Martin Kakan, who is the NASA pilot of the Ingenuity helicopter on Mars. He is going to be right here in this little room talking to us. He happens to be Jerry Wilson's, we got a video on this? He's Jerry Wilson's godson. So I got questions of the man, and I guess they retired the little drone on Mars. It's with Perseverance. That'll be the 10th. We don't have it on the first Friday because that's 4th of July. And we don't have it on the second Friday, which would be the 11th. It got moved. I'm not sure if something they're doing here function. Friday, August 2nd, to complete the summer, Dr. Stephen Kane on planetary habitability in the solar system and beyond. He's an expert on Venus, and he comes from I think UC Riverside. And then we're working on the fall. So right now, let me tell you about this lady. Looks like a lot of fun. I bet she's the most popular professor on the campus at CSU San Bernardino. Dr. Maria Katy Rodriguez-Wimberly, assistant prof with expertise in near-field cosmology and galaxy evolution. She's also a director of mentorship for Cal Bridges program, a CSU-UC STEM scholarship source. Dr. Wimberly continues her service on the board of directors for the Astronomical Society of the Pacific. She's a Southern California native, went from Mount San Antonio College to CSU Long Beach, where she earned her physics BS and then her physics PhD from UC Irvine. Completed a postdoc at UC Riverside, where she was a National Science Foundation Math and Physical Sciences Ascend postdoctoral pre-research fellow. I've run out of space and I'm right real small at the bottom. Let's welcome her up to talk about ultra-faint dwarf galaxies and evolution. Dr. Katy, please.
Thank you. Okay, so now I need to share. Oh,
Barbara, I want to introduce your husband.
my lovely husband, Chris Wimberly, has come with me. He chauffeured me here. Thank you. And I'm fairly certain all of the people on Zoom are my sisters. So thanks. All right, so I will get going. I'm so thankful for the Santa Barbara Astronomical Unit for inviting me here. I'm really excited to chat with all of you about ultra-faint dwarf galaxies and talk a little bit about their kind of galaxy evolution in general. So what do I mean by ultra-faint? For those of you who were just in the planetarium show, and really for everyone, we know what big, beautiful galaxies are, right? So I want everyone to just take a second, close your eyes, picture a galaxy. What do you see? What's in the galaxy? What's the structure of the galaxy? What's the color of the galaxies? Okay, did anyone see, yes, I want to stay muted, sorry. Who saw something like this? Yes, right, okay, yeah. And I think this is actually one of the galaxies that we saw in the planetarium show.
Can you unmute?
Yes. Okay. Okay, keep going. So these are active galaxies, all of those spots of pink and white. There's new stars forming in those galaxies. This is a spiral galaxy. Many of the galaxies we see out in the night sky, both with our naked eye and telescopes, look like this. Big, bright, and beautiful. There's a lot going on. They're fun to look at. By the end of this talk, I promise you that you will think, this galaxy is just as exciting. And I promise it's a galaxy. So this is an ultra-faint dwarf galaxy. This is Leo 4. That kind of, let's see, can you see my cursor? You can. This dashed yellow line is the extent of where we think that the stars in that galaxy kind of reside. And this zoom in there from the Hubble Space Telescope shows the inner core of stars that we really have detailed information for. I'll talk about this galaxy a little more and show you why it is actually a galaxy. I promise it is. So this is what I mean by ultra-faint, right? No one look at that and go, yeah, that's a galaxy. They're also ultra-small. small. So you may be familiar with these kind of 2-scale models of the solar system, right? If you think of a giant like beach ball kind of thing, that would be the size of the sun, and some tiny little marble would be the size of Earth in this scale model. Keep that kind of difference in mind. Giant beach ball, tiny marble, and replace the sun with our own galaxy, the Milky Way, then the tiny marble would be an ultra-faint dwarf galaxy. That is how much smaller these galaxies are compared to our own galaxy, the Milky Way. And for one more point of reference, the Milky Way is actually just a medium-sized galaxy. There's galaxies that are hundreds of times larger, even more, than the Milky Way. So we're just average size. These are the smallest galaxies that we know of. And partially because of this, how small they are, how faint they are, all of these galaxies that we have discovered are satellites of the Milky Way. And it's because of digital sky surveys, like the Sloan Digital Sky Survey, that in 2005 we started finding a whole new crop of galaxies that orbit around our own galaxy, the Milky Way. So this, I'll let it play one more time. So in the night sky, we can see in the southern hemisphere primarily the large and small Magellanic Clouds. As our telescope technology started to advance, we saw more what we call dwarf galaxies, and then there was decades where we didn't really discover any new galaxies orbiting our own until these digital sky surveys. So really technological advances is why we know about these ultra-faint dwarf galaxies. And what do I mean by satellite? So we think every single galaxy, and actually a criteria for a group of stars to be a galaxy, is that they have to live in a dark matter halo. So this is just kind of a graphical representation, right? We think a dark matter halo is literally like a ball of dark matter with a galaxy inside of it. Every single galaxy has these dark matter halos, large ones, and even our ultra-faint dwarf galaxies, itty-bitty ones. And just like kind of everything else out in space, as everything's moving around, tiny galaxies are attracted or gravitationally pulled in to larger galaxies. So as soon as you have this kind of nested galaxy, nested dark halo situation, we kind of reclassify them and call the smaller galaxies satellite galaxies and the larger galaxies the host. So the host galaxy is the largest in the group, right? We're a host galaxy, and then we have what we think of as now 60-ish satellite galaxies. Before the Sloan Digital Sky Survey, we had about 10. So we've jumped up about 50 ultra-faint dwarf galaxies are all satellites. So why do we think these ultra-faint, ultra-small Milky Way satellites are so cool? Because they may be fossils of the very first galaxies ever formed in the entire universe. Relics from the early universe, the first structures that formed, we think. So we can use them in this sense as a tool in near-field cosmology. So cosmology, we know, is all of the really amazing stuff that the James Webb Space Telescope is discovering, looking back as far as we possibly can into both time and space, back into history. And that's great, but we're getting really fuzzy pictures of little red dots that we're like, that's a galaxy, I promise. What we do in near-field cosmology is look at things that are really, really close to us in great detail, but they're just really old things like galaxy fossils. So it's kind of like galactic archaeology in a sense. So we look at today to see into the past. But to be able to do this, we have to make sure that these tiny systems in our galactic backyard are actually relics of the first galaxies ever formed. So they have to be a galaxy. We'll talk about that. And you saw the picture. They don't really look like galaxies sometimes. So there's a lot of work to confirm that they're actually galaxies. To be a relic, we want there to be no real evolution since the early universe. So they formed all of their stars and stopped forming new stars before what we think of as the early universe ended and kind of transitioned into what we call the modern universe, where we just see galaxies and stars evolving as we see them today in our own system. So no evolution, they have to be a galaxy, and in part of this, they kind of have to be lonely too. We know galaxies merge a lot, right? And we've seen that in many galaxies come in like pairs in a sense, and they start merging. That merging can affect what the galaxy looks like. So if we want a pristine fossil, we have to find something that's been lonely since the beginning of the universe. For about 12 billion years, it needs to have been pretty lonely, 10 billion years, right? So a lot of the work in ultra-faint dwarf galaxies is kind of checking off these three requirements. So let's first look at why they need to be galaxies. There are other groups of stars out in the universe that are as small as they are. These are three examples of globular clusters. Globular clusters and ultra-faint dwarf galaxies are generally the same size. A little more compact globular clusters are, and when you visually compare them, ultra-faint dwarf galaxies are ultra-faint, right? Has it in their name. The biggest difference here is that with globular clusters, we can look at the velocities of the stars across the globular cluster, and there's no evidence of dark matter in the globular clusters. So the globular cluster isn't housed within that dark matter halo like our ultra-faint dwarf galaxies are. And that's the kind of main criteria. We can look at the stars in a galaxy that seem to be this, what we call an overdensity of stars, so just a group of stars together. We look at their velocities. They all have really, really tight velocities, right? So they're all very correlated here. All of these red lines are velocities for stars in this system, Ursa Major 1. They also have to be physically close, right? So we know they're orbiting each other. We know they live in that dark matter halo. And then we can compare all of the colors of the stars. So on this vertical axis, we have one color in the R band. It's just a little slice of the full optical wavelength range that we can see. Down here on the horizontal, we have G minus I, which is the same thing, just different slices subtracted from one another. Astronomers call this color. We're real fun sometimes. But we can compare what we see in the galaxy to what we think sets of stars that are ancient or different ages should be. And so this shows us a little hint that all of these stars are about the same age, because the models, the red and blue lines, match the member stars in this system. So these three things are what we use to determine whether these groups of stars are galaxies or not. Do you have a question? Do you want to ask a question now?
I'll have one.
Okay, yeah.
You answered part of it, but what I was gonna ask, globular clusters, star clusters, same thing, right?
Yes.
Captured small galaxies, they're in our galaxy, but they're the same size, and some of them actually were separate galaxies, right?
Yeah, so there are the Milky Way's stellar halo has a lot of destroyed ultra-faint dwarf galaxies in it. And some of the clusters, we believe, that are kind of in the halo may have originally come from an ultra-faint dwarf galaxy that just got ripped up and is now floating around our stellar halo.
But dark matter, they don't have dark matter in them?
So technically there's dark matter throughout them, but they don't have their own sphere of dark matter that they're living within.
I think we can see that stuff.
Yeah, so it's through the velocities that we see it.
I gotcha.
Yeah.
Right.
Yeah, nice. Yes.
Sorry, since we're asking questions, when you say similar velocities, are you talking about like the entire galaxy moving in one direction, or are you talking about the expanse of a particular galaxy? What's the velocity?
Oh, the velocities of the stars in our line of sight. So all of those stars are kind of moving towards or away from us at the same speed-ish. Yeah, nice. Other questions since we're at break? Okay, I'll keep going. But yes, feel free to shut me up, raise your hand, and I'm happy to answer your questions. Okay, so we have 3 ways that we kind of dictate whether these are galaxies or not. Most of them are, so we can keep on going. We kind of have our first check off. Yes, they're galaxies. We can think of them as potentially fossils of the first galaxies. With any fossil, we want it to be very pristine, right? We don't want it to have much evolution. So this is work that I did during my graduate program at UC Irvine, where we looked at these star formation histories of 6 of the ultrafaints in our satellites. So on the horizontal axis, you have like when those stars were formed, and that vertical axis is just a fancy way to say how much of the stars in the galaxy formed over that time, right? So we can read all of these, and I can move this along. We can see that all of these systems, all 6 of these systems, had about 100% of their stars that we currently see today formed 10 billion years ago. So all of these stars are at least 10 billion years old. They're all universally ancient. That means all of these galaxies formed about the same time and stopped forming new stars about the same time. This would mean that they could be these ancient, pristine fossils. But, again, going back to this idea of merging galaxies, if a small galaxy becomes a satellite of a larger galaxy, the environment of that larger galaxy can stop the star formation, new stars from forming in that galaxy, in the smaller galaxy. So what I did in grad school was use really awesome cosmological dark matter only simulations that literally start from like as early in the universe as they can and just form what we think the universe looks like. That's a cosmological simulation. This one is showing 2 massive galaxies, and then every single other little dot there is a smaller what we call a satellite galaxy, a galaxy that's in the gravitational pull of the 2 largest ones. This is also showing some of the gas and dust around those galaxies as well. So I went into simulations like this, found the little ultrafaints, and kind of tracked what they did throughout their evolution to see if the large galaxies, like the Milky Way, shut off their star formation. So did they have evolution after their initial ancient stars formed? And what I was able to show in simulations like this is that there's no, to have giant populations of ultra-faint dwarf galaxies that all have ancient stars, the Milky Way and other large galaxies did not have an effect on their star formation. So they're orbiting around us today, but we haven't affected their evolution a lot. So, they're galaxies, they haven't had much evolution. We know that they're not lonely because the ones we know of are around us, but there's other large galaxies near us, like the large and small Magellanic Clouds, which are still much larger than the ultrafaints, right? So work that I'm doing now is looking at how we can use the elements or the different chemicals in stars to learn about how these galaxies evolved as they moved through being satellites of different larger galaxies. What's great is that the periodic table not only tells us all of the elements, every single thing in the universe, right? We know where all these elements were made. Many of them are made in dying high mass stars. Some of them are made in these white dwarf supernova. So when the white dwarf in a binary pair. So if you have a massive star and a white dwarf, it'll go nova every once in a while, like the one that we'll see hopefully soon. At some point, that little white dwarf will get tired of going nova and actually go supernova. When it fully explodes, there's a lot of new, what we call heavy elements created in that supernova. So when stars die, we get a lot of cool stuff. And there's a few elements, like hydrogen and helium. Those were created in the Big Bang. They are created in stars also, but we can track the kind of evolution of the universe through stars dying. And we can take it a step further and try to figure out if we can see remnants of some of the first supernova or some of the first stars to die by looking at kind of ratios of different elements in these stars. So I've kind of highlighted magnesium, which is formed primarily in dying high mass stars, and titanium, which is formed in those white dwarf supernova, right? So if we see titanium and magnesium in a star, we know there's different events occurring prior to the creation of those elements that are creating the elements that we see today. We can use this to trace the chemical evolution of an ultra-faint dwarf galaxy, or any galaxy. So I'm doing that right now with Hydrus 1. This is kind of just what we now like to call a run-of-the-mill ultra-faint. It looks like every other one, all 50 that we know of. We have data from the Magellan telescope in Chile for 10 of the stars in Hydrus 1. And I know 10 stars in a galaxy is not that exciting, but when we're talking about ultra-faints, we're doing good. The most data that we have for any galaxy, any ultra-faint dwarf galaxy is a whopping 15 stars, so 10 is pretty good. We have spectroscopic data, so I go into the data, look at all of the kind of emission lines from the stars, and I can measure how much of an element, or these different elements, are in that star. So this is a kind of element abundance figure. I know it looks a little technical. On the horizontal axis here, this is looking at iron divided by hydrogen. What we're really using that for, astronomers, we like to call anything that is not hydrogen or helium a metal. Yep, a metal. So we use the fraction of hydrogen in that star, we use the fraction of iron in a star divided by the fraction of hydrogen in a star as a way to talk about metallicity. So this is how much stuff is in the star that isn't hydrogen or helium, right? And because these stars are universally ancient, we can use that metallicity value as kind of a proxy for age. So this brown star here that has a higher metallicity is the youngest of these 10 stars. And then this vertical axis, we're taking the carbon, so the amount of carbon in that star, dividing it by the amount of iron in that star to just kind of be able to compare all of these elements to the age of the stars. These bright, colorful markers are the stars in Hydrus, and all of those gray small markers behind it are other stars in ultra-faint dwarf galaxies. So yes, Hydrus looks like all the other ultra-faints, which means we can use it and all the other ultra-faints as tools in near-field cosmology because they all look the same, right? We're getting towards this great pristine fossils. What's interesting about Hydrus 1 is if we take that ratio of magnesium, so elements formed in dying high mass stars, and compare it to the ratio of titanium, or elements formed in white dwarf supernova, we see something really interesting here. So these two, the youngest stars in the system, have very different ratios of magnesium to titanium, which points to the possibility of there being, of the star formation events, so dying high mass star, white dwarf supernova, not mixing very well in the early universe. So this is where those two stars lie in the galaxy. They're kind of on opposite ends, right? If they stayed in that sort of rotation, you know, got all of the stars are orbiting around, but if they stayed far apart from each other, and they've always been far apart from each other, then when those stars formed, it means the white dwarf supernova that went off in one area of the galaxy didn't really mix throughout the entire galaxy when at a similar time when the dying high mass star went off. So we're seeing, just from these two stars, events in the early universe that are acting slightly differently than we think happens today. So this may be evidence that the early universe acted different than what we see today. And this is why these ultra-faint dwarf galaxies are so cool, is that just from two little stars, we get to see what's happening in the early universe. So they're mostly lonely. That means we can use these awesome things as tools in near-field cosmology. And I'm continuing this work now at Cal State San Bernardino. I'm looking at a galaxy called Willman 1. This is a galaxy we've known, well, I should do galaxy. We've known about for since about 2011, which in ultra-faint terms is very old. But you can see in these two figures, it kind of lives in this weird area. So here we have just the size of the galaxy, down here, how bright the systems are. These are all galaxies. These are all globular clusters. It's right there at the intersection. So we can't just look at its size or how bright it is to tell if it's a galaxy or not. And we can do the same thing with, this is a kind of way to talk about how fast the stars in the galaxy are going, how bright it is. It kind of lives here at the edge of the brightness where we don't know what's happening with any of those systems. So even though we know of around 50 ultra-faint dwarf galaxies now, even some of the galaxies that we've known about for the longest time, we still don't know if they're actually galaxies. And we see this when we look at oh goodness, no one wants to see that. Okay, here we go. If we look at the kind of mass of galaxies, of satellite galaxies, so these are tiny, tiny galaxies. These are our classical dwarf galaxies, so those first 10 galaxies that we discovered orbiting around the Milky Way. And we look at the relationship of the size to them compared to their kind of metallicity, right? All of the different elements in those galaxies. Up here, fairly well behaved, our observations compared to our simulations, which are the black lines, our models, and the simulations, which are the blue dots. But when we get down here to the smallest galaxies, our models and what we see just are not friends. They don't mix at all. So I'm looking at all of these systems through spectrographs and telescopes to try to figure out what is happening. Are these galaxies? Are they remnants of galaxies that got ripped apart and all we're seeing is this little kind of dead inner shell of them? Or are we mischaracterizing actual faint globular clusters as galaxies? And what's really exciting is we can do this work right now. We have, data for 5 of these. There's folks getting data for more, but this is kind of a visual representation, a graph representation of the video I showed y'all earlier. As we move forward into the 2020s, 2030s, we're just gonna discover more and more of these ultra-faint systems, both within our own galaxy, the Milky Way, but even within nearby large galaxies like Andromeda. So when the Vera Rubin Observatory, it's going through its kind of first light processes now, it's gonna start taking data and finding just tens and hundreds, maybe even thousands of these systems. And hopefully, if and when the Nancy Grace Roman Space Telescope launches, it's set to launch in 2027, but we all know how the NASA's budget's going, so.
Extinction level event.
Yep.
Yeah, exactly. So, call your representative, tell them to launch Nancy Grace Roman so we can keep finding more ultra-faint dwarf galaxies. Thank you so much for listening to me, and I'm really happy now to talk to y'all, take questions. Thank you. Yes, okay, so I'm hand in the back.
Yep, so question, help me understand when you say these ultra-faint dwarf galaxies are orbiting around our galaxy, order of magnitude, are they very close, so they're passing through our galaxy periodically, or they're like, multiples of the radius of our galaxy, and they are truly pretty far from our galaxy, attached by gravity, but they're really not interacting with the gravity, passing through our galaxy at any time, because they're too far out.
Yeah, so the closest ones that we've seen, we think there are some that have actually passed through,
Okay.
but the majority of those get destroyed and actually
Okay.
just kind of become part of our stellar halo.
So those wouldn't pass your lonely test.
Correct.
Got it.
Yeah.
Got it.
Yeah.
Okay, so most of these then that are truly lonely are probably far enough out. They are not interacting
Exactly.
with us.
Yeah.
Got it.
Yes.
Thanks.
Yeah. Yes. Here in the moment.
It sounds like you're using, excuse me, my voice is going, you're using the biggest telescopes available. Which telescopes did you use for this data?
These were for, Hydrus 1, we use the Magellan telescopes in Chile. They're about 6 meters. And then for Woman 1, we use the Keck telescopes in Hawaii, which is 10 meter.
Okay.
Yeah, so hefty, but I guess Keck is still technically the largest. The European European Southern Observatory is creating the extremely large telescope, which will be 39 meters.
And the giant Magellan, was it?
Oh yeah, Giant Magellan telescope.
I don't know, I've heard
Yeah.
of it, but- The Gaia? No.
No, that's
It's
small.
over there, the
We do
Gaia.
use Gaia. We love Gaia. But yeah, Gaia's in space.
Yeah, well, it's still up there.
Mhm.
But it shut down, I thought.
No, it's still going.
No, it just shut down.
Oh, did it?
Yeah. But they haven't done the last data release yet.
Oh, okay, that's right. Yes.
Speaking of little space telescopes, the Sphere-X went up in February, and I think they got its first data. It's only 20 centimeters. Can you use the spectroscopy from that?
I think we could. I haven't looked into it because I know that a lot of its mission is more like high, it's cosmology based, but trying to look a little bit further back.
Right.
So when it's open to kind of anything, there's a possibility, and there's folks that are trying to use JWST's spectrograph that's not great for chemical abundances, but they're trying to make it work. But yeah, so Sphere-X would definitely be something we would want to look into. Yeah. Yes, here.
Dark matter halos, how are you determining that? And that's question one.
Yeah.
Question two is our huge galaxy have a dark matter halo?
It does.
Oh, it does?
Yeah.
And how do we determine that?
So with spiral galaxies, it's fairly easy. If we look at the velocity of all of the stars going from the center of the galaxy all the way out to the edge of the disk, and we predict what we should see, how the velocity should kind of decline the further out from the center you are, they don't. They just flatten out. So the difference from what we see, which is the flattening, and what we expect, which is the dip, that difference is what we call dark matter.
Okay. And you have the same kind of thing happening for the small galaxies?
Yeah, so because there's not really clearly defined structure in the smaller galaxies, we're not measuring that kind of velocity change. But what we do is similarly use the velocities to try to measure what we think should be there versus how the stars are moving, so what we see is there. Yeah. Yes.
Some of your slides mentioned reionization.
Yes.
Is that an event in the universe's evolution, and what does it mean?
Yes, it is. That's an awesome question. So something called the reionization epoch. And reionization is slightly a misnomer in a sense. So when the first atoms formed, you had neutral atoms, which was like primarily hydrogen and helium. And hydrogen, a neutral hydrogen atom is a proton. So if you have a proton with no electron around it, it's a neutral hydrogen atom. So reionization is the first time in the universe when after electrons had kind of attached themselves to nuclei, so hydrogen and helium primarily, when those electrons were able to kind of bounce out and leave that atom, so ionizing the atom, it lost an electron. So there was an era of the early universe where we think this was happening just throughout space. Many atoms were losing their electrons because they were kind of spread out enough and there's enough space for light to start to travel and hit those atoms, electrons left. During that time, there was a lot of star formation, and we think that's when all of these galaxies formed their stars and then stopped forming their stars during that era. Nice. Oh yes, there is, yes.
Over time, will some of these dwarf galaxies merge with the larger galaxies that they're circling around?
We do see evidence of that in some of the, so in the Milky Way, in our stellar halo, we see things called stellar streams. And so we can, if you think about like that relationship between the velocity that we see in the intact galaxies, there's these kind of groups of stars or streams of stars in our halo that have that same relationship. So we can model that and show that that used to be an ultra-faint dwarf galaxy. Yeah, nice. And there's, yes.
Is your research one of the ways you can prove that dark matter actually exists?
We're trying, yes. So one of, looking at ultra-faint dwarf galaxies, these are, and I didn't mention it in the talk, these are the most dark matter dominated systems in the universe, at least that we know of. So compared to the number of stars that we see and the mass of those stars, and then the mass of the dark matter that should be surrounding it, there's much more dark matter compared to visible matter. So there's a lot of folks that are trying to see kind of evidence of dark matter, and they look at ultra-faint dwarf galaxies. So the better that we can kind of characterize the velocity of the stars in the systems, the better we can like pinpoint laboratories for dark matter discovery.
Dr. Katy, one of our more esteemed members in the middle is about to ask you a question. He's our head of City College Astronomy Department. Dr. Sean Kelly, what did you want to add?
I was just curious, is there evidence of black holes in the centers of these?
We have not seen any evidence.
Okay.
We don't see any gas and dust, but that's another, like, at least in the simulations. So there's a group at Cal Poly Pomona that's trying to simulate these to see, like, do they have a black hole, and like, is there a way that we could see it now, even though we don't see any dust in those systems?
Yeah, you heard about James Webb, and the most earliest galaxies may have supermassive black holes already.
Yeah. Right, it'd be so cool.
So you're looking for any activity, anything that might show the black hole?
Exactly, yeah.
Thanks.
Yeah, yes.
I've got a question. If these things are orbiting pretty near the Milky Way galaxy and they're 11 billion or so years old, why is it they haven't been sucked into the big galaxy long ago? How is it that they're staying out there?
So part of it is just the randomness of the orbits, right? So we think, we can see this in the simulations, that there's so many ultra-faint dwarf galaxies. We've only seen 50 of them, but there's so many that they're constantly there's constantly ultra-faints becoming new satellites of the Milky Way. So there's plenty that have merged with our galaxy, and we see remnants of them in our stellar halo. But there's so many throughout the universe that there are new satellites of the Milky Way all the time. So at some point they may all fall into a larger galaxy, but at least right now in kind of cosmic time, there's plenty that still exist. Yes?
How far we can reach in the cosmos?
So JWST thinks it goes back pretty far. I don't know, I haven't been following how far it goes back, and let me think if I can translate it. So we think we can see some evidence of galaxies at the like very, very tail end of that reionization epoch. And that's a lot of the work that JWST is doing, looking for those. And part of the reason these systems are so exciting is they may have been formed earlier than that. But seeing into that very early period is difficult because of how much activity was going on. So technologically, we're not quite there, I think. And, yes?
Yes, I wanted to build on Sean's question. So when you say that more of these ultra-faint galaxies are joining the ones that are orbiting, does that mean there are more just wandering out in the universe that currently aren't attached to a bigger galaxy?
Yes, and that we're pretty sure they exist. So there's one ultra-faint that we see, it's called Eridanus 2. We think it lives right outside of the Milky Way's dark matter halo. There's some argument about how wide our dark matter halo is and where it is, but it's like right on the cusp. And there's been some work to show that it may not have fallen in yet. Because satellite galaxies can fall into a dark matter halo, orbit around for a little bit, and then leave. We call those splashback galaxies. So Eridanus 2, we think, may not be a splashback galaxy, just hasn't fallen in yet. But yeah, there should be all over the place, the ultra-faints. Yes?
So you're doing the elemental abundances from spectra, right?
Yes.
And capturing spectra takes a heck of a lot longer than capturing images.
Yeah.
And so trying to get spectra of ultra-faint galaxies sounds like a real challenge. How long of exposures do you need?
So for those stars, it was about 8 hours per star.
Okay.
We take it in like 30-minute images and just stack those images together. But multiple nights per star for about 8 hours.
And that's at a very large aperture.
Yes, and very clear skies. So lots of tries, and in some of they had the error bars that come out of the markers are real big, and that's part of the reason why, because you get one stray cloud and your whole night's shot. Yeah. Yes.
Yeah, I was going to ask, but you're mentioning you're using just really large apertures. If you could use the Las Cumbres Observatory telescopes to watch continuously and accumulate spectra that way. But if you need a really big telescope, they don't have them yet.
Yeah, exactly. That's kind of where we're at. And there's some work trying to figure out how to use smaller telescopes to get it, or lower resolution spectrographs. But that's in the kind of infancy of like advancing that technology. Yes.
How do you even recognize one of these things? When you've taken a picture of a star field, I mean, the pictures you showed look like nothing.
Yeah, it's basically AI. So I mean, kind of AI, but not really. So the Sloan Digital Sky Survey, these giant digital surveys, right, that just are dumping data upon data. The observers write like machine learning algorithms to just run through everything and try to find these like overdensities. So where is there a group of stars that we don't see, but they are actually close together? We just, aren't attuned to it, I guess, in a sense. So yeah, machine learning algorithms find them first, and then we visually confirm that they're there. Yes.
How the universe extending from a center point or myriads of center points?
Oh, that's a good one. So, I mean, we don't, I think the Big Bang Theory says that we started from one point and went out, but we don't know what started that point, so could be anything. Which is kind of exciting and weird.
What is the night sky in San Bernardino like?
It's fairly hazy a lot of the time. So we actually have a 17-inch and a 24-inch telescope, and we try to go out there all the time, but where we are in San Bernardino, we're right on the San Andreas Fault, which is also real fun. Our poor telescopes are like right on the fault. So we do get some very clear nights, but there's a lot of haze out there.
Are you on the way to Mount Wilson?
Kind of, if you keep on going, I guess that would be east, following the mountain range.
I don't know that much about the Inland Empire. Riverside is south of you, right?
Yes.
That's another county.
Yes.
Okay, our August speaker comes from there. Do you happen to know him?
I do. He's very nice.
Really?
I'm excited for you all.
Okay, and we'll talk about, have you ever seen his speech?
I have not got to see his talk.
Habitability on other planets.
Yeah, that's so cool.
Venus mostly. One final question. This is a great speech. Let's give her a hand.
That there are many livable planets in the universe, and could be like human life, and could be many other areas, like many interesting different forms living.
Yeah.
And one, we might meet them in our life, we might not.
Might be some here tonight. I would like to take this moment, Dr. Katy Rodriguez-Wimberly.
I love it, thank you.
To present you with our Sacred Club, Ceramic Club.
Wonderful.
If you hold on to this and don't use it for several years, it'll be worth the same it's worth now, $10.
Why don't you go along? Because it's easier.
I should, but I prefer doing this.
Kill the wires. Andy, you doing good?
Yeah, how are you?
Hang in there.
Don't forget, next month we will not have a speaker or a meeting, we will have a pop-up. Please get out your recipes and join us. Good night.
So I've seen that that orange celestial